In this video, we will talk about the row space of a vector. What is the row space? Well, it is the set of all linear combinations of the row vectors in A. So if A is m by n, then each row vector is a subspace of Rn, which makes perfect sense. Now, notice here we have vector A, and A is obviously a 4 by 3. And notice each of my row vectors, and I want you to note the notation. You can either write it as your textbook writes it, which is 302, or you can write it as a vector 302, which is my preferred method because I think commas are silly. So you can write it like this. Also, if you'll note down here, we can write the column space of A transpose for the row space of A. So this is the row space of A, or I could write it with this notation, or I could write the column space of A transpose. So remember, A transpose would just be turning my rows to columns and columns to rows. 4, 0, -7. And then the column space of A transpose would be 302, 1, -1, 3, 2, -1, 5, 4, 0, 7, assuming these are all linearly independent, which we would have to do a little bit of math to figure out, because either way we do this, we're really going to want to reduce this to echelon form. But we get the idea here that that is essentially what the row space is going to look like, which is the transpose of that is the column space. Before we actually do a practice like this together, I want to talk about this theorem that tells us that if A and B are row equivalent, then the row space of A is equal to the row space of B. And that if B is an echelon form, as my B certainly is, then the non-zero rows of B form a basis for row A and row B. So first let's just find row A, given that the row space of A, given that A is row equivalent to B. Well, if A is row equivalent to B, all I'm doing is looking for the non-zero rows. So the row space of A is equal to the row space of B, and the row space of B is, and again, depending on how you want to write this, I can use parentheses and commas, and that's the way your textbook shows. And then 0, 1, 0. Or I could write them as the transpose, and it really doesn't matter either way that you do it. But that would be the row space of A and the row space of B, because they are equal. And again, if they ask us to find a basis, well, this is also, in this case, the basis, because we don't need anything just like before in the spanning set theorem. We're able to take away those columns that are redundant. We can take out rows that are all zeros as they do not belong in the basis. Here's a great practice to work on together, and it's going to help us with concepts that we already know, and of course our new concept of the row space of A. But notice I've given you A, which is the original matrix. Then you would reduce that to echelon form and then reduced row echelon form through row operations. And here's why I've given you all three. So normally I would just give you A and make you do the work yourself, but we only have so much space to show work. So let's start with the basis for the row space of A. So the basis for the row space of A, remember, requires us to have our matrix in echelon form, because I need to know if I have any rows of zeros. Because if it's a row of zeros, I can take it out, and my basis is just whatever's left over, which is 1, 0, -1, 5, and 0, -2, 5, -6. And keep in mind your textbook will have this instead written as 1, 0, -1, 5 with parentheses and a comma, 0, -2, 5, -6, and both of those answers are fine. My fat fingered that, so there we go. That is the basis for the row space of A. So the basis for the column space of A, oops, forgot my C, C-O-L-A. So the basis for the column space of A requires us to know which columns are pivot columns, which I can tell here, and I could kind of tell here as well, but I like to get it all the way to reduced row echelon form. So I know that column 1 and column 2 are my pivot columns. So the basis for the column space of A is the original columns 1 and 2. So that is the basis for the column space of A. It's the pivot columns, but it's the original pivot columns. And then, of course, we've got our null space. And if you'll recall, the null space of A is found by saying that AX is equal to 0. And so essentially what I have here is my reduced row echelon form, which tells me that x1 minus 3x3, I'm sorry, minus 1x3. Oh, goodness. x1 minus x3 plus 5x4 equals 0, because remember we would just have an augmented 0. And that x2 is minus 5 halves x3 plus 3x4 is equal to 0. And so to find my solution, I would write it in terms of the free variables, which are obviously x3 and x4. And so x would be x3, and then, oops, let's go ahead and rearrange these. So equals negative, oh, that was a negative, equals positive and negative, and then the equals and positive, and change that guy to a negative, because we want x1 and x2 in terms of the free variables. So for x3, I would have 1 x3, I would have 5 halves x3, I would have 1, because that's the free variable, and then 0. And then for x4, I would have -5, -3, 0, 1. So the basis for the null space of A would be those 1, 5 halves, 1, 0, and -5, -3, 0, 1. So good job. That's putting together a lot of things that we already knew and a little bit that we didn't. Here's a practice for you to try. Again, I was nice enough to give you all 3 forms already. So I want you to find the bases for row A, column A, and null A. Press pause, try those questions. When you're ready, press play to see how you did. So again, if I'm looking for the basis for the row space of A, I'm looking at the echelon form and just getting rid of any rows of zeros. So my basis for the row space of A is all of the rows that are not all zeros. So that is going to be 1, 3, -5, 1, 5, 0, 1, -2, 2, -7, and 0, 0, 0, -4, 20. So again, I'm looking at echelon form when I write my basis for the row space of A. The basis for the column space of A comes from finding where my pivot columns are, which I can see both here and here. So either echelon or reduced row echelon. that is all we need really for row A, and column A is just echelon form. It doesn't have to be reduced row echelon form. So the basis for the column space of A is going to be any of the original columns for the pivot columns. So my original column, let's stick with yellow, for column 1, which is a pivot column, is -2, 1, 3, 1. For column 2 is -5, 3, 11, 7. And for column 4 is 0, 1, 7, 5. So that is the basis for the column space of A and previously for the row space of A. Now what we have to do is look for the null space of A. And remember, the null space of A does require a little bit more because I'm looking at each row that's not all zeros here and saying x1, so my free variables are x3 and x5. So basically I want to write x1 in terms of x3 and x5 and x2, etc., etc. So x1 is equal to negative x3 minus x5. x2 is equal to positive 2x3 minus 3x5. And x4 is equal to 5x5. And that's all I have to do for that. Now, if you'll recall, I'm thinking about my solution in terms of x1, I'm sorry, not x1, x3, and then I'm going to have negative 1x3, 2x3, 1, because x3 itself is the free variable, x4 is 5, and then of course 0 x5s. And then x5 would be negative 1, negative 3, 0, 5. Whoopsies, I screwed this one up. Somebody help me. This should have been a 0. So negative 1, negative 3, 0, 5, and 1. And again, this should have been, that looks like a weird, this is a 1 and then a 0 because this was 5x5. I read it as 5x3. So that's how I would write my solution, which means my basis for the null space of A is just those two vectors, which is -1, 2, 1, 0, 0, and -1, -3, 0, 5, 1. Done and done. Hopefully you did well on that one.